Washington State University. Go Cougs!
Hello everyone, in this video I'm going to cover lesson 5 of Python for Data Analytics, where we're going to talk about the pandas module and specifically the series object in the pandas library. So from the pandas website, pandas is described as an open source BSD licensed library providing high performance, easy to use data structures and data analysis tools for Python. Now, this may sound familiar to NumPy, and in fact, pandas is built on top of NumPy. The key difference between NumPy and pandas in terms of their objects is that pandas have axes that are labeled, which is going to be incredibly helpful for working with activity and health data and data analytics in general. There are 3 main data structures in the pandas library: series, data frame, and panel. We'll spend most of our time working with series and data frame. So let's get started working with series in this lesson, and then in the next lesson we'll talk about data frames. So just like how we had to import NumPy as NP in order to gain access to NumPy, we need to import pandas, and it's traditionally imported as PD. So moving on, now that we have pandas imported, we can go ahead and create a series. So a series is a one-dimensional labeled array. The axis labels are collectively referred to as the index, and the index values need to be unique. That's because the index is going to map to an item in the series. You can think about a series as being an ordered dictionary or a list or an ND array where instead of being restricted to integer zero-based indices to select items, we can specify any unique indices to specify items. So I'm going to work with an example where we're going to construct a series where the index is going to be names of cities and the values are going to be populations for those cities. And I've selected cities that are in Washington State, the home of Washington State University. So let's construct a Python dictionary that's going to store this information. So let's start with Seattle. So Seattle, the key is going to map to the value 652,405, which is the population. And let's continue on. Spokane will map to 210,721. Bellevue, 133,992. And lastly, I just grabbed a small town, the wonderful town of Leavenworth, Washington, 1992, 1,992 people living in Leavenworth. So let's go ahead and construct a series from this dictionary. Now, dictionaries are inherently unordered. So when we construct a series from a dictionary, the index is going to be ordered, in this case, alphabetically, since our keys are strings. So I'm going to just use ser for short for series. It's going to get pd.series, so invoking the series constructor for my dictionary. And then let's go ahead and print out ser. Now, we see 2 columns of information. This first column is our index, and note how it has been sorted alphabetically. Our second column is the value that this index in the same row maps to. So for example, Leavenworth maps to 1992. So you can get a sense of what a series looks like by seeing this kind of column or key value pair representation. And down here, our data type is N64. And this is the data type for the values of the series, which is our population. These are all entered in as integers. So let's take a look at an alternative way to construct a Pandas series using a list or an ND array. So let's have a list of, say, range 1 through 5. So this will give us 1, 2, 3, 4. And let's make a series from this data. Okay, so here's our data. Let's print out our series of it. And since we didn't specify that there's an index like we had naturally with our dictionary, then just natural numbers starting at 0 are assigned as our keys or our index for our data, 1, 2, 3, 4. Now, this kind of just looks like normal zero-based integer positional indices for an array, such as an ND array, or a list. Now let's take a look at working with some random data. So let's import NumPy as NP, and let's overwrite data with random values. We'll say 5 values, and let's overwrite ser with a series representation of this random data. And here we see our natural ordering 0 through 4 and our random data. So by default, like I said, we're going to have integer values as our indices, but we can also explicitly set our values for our indices at instantiation time when we call the Pandas series constructor. So instead of 0, 1, 2, 3, 4, 5, etc., let's use letters of the alphabet, such as A, B, C, D, etc. So I'm going to import string, and I'm going to grab 5 letters from the alphabet, the first 5. So I'll get ASCII lowercase, which is a string of all the lowercase ASCII letters A through Z, and I'm just going to grab the first 5. Let's create data again, just get some new random data, 5, so this will be the same length as my soon-to-be index alpha. And ser is assigned pd.series, and we're going to make this of data and explicitly set the index to be alpha instead of 0 through 4. And we print out ser, and now we see A through E as our index instead of 0 through 4. Now let's return to our previous example where we were working with the city population pairs for city populations in Washington State, and we made a series out of it. Run this again, and we see that even though we know the index represents a city and the values represent populations, we don't have those labels associated with our series. And I mentioned earlier that we're going to have labels for our pandas objects. So let's take a look at how we can add labels to our indices and to our values. So let's set ser.name to be population. So the name of this series is now population. That's what it represents. And the series.index.name, so now we're going to name the index, is going to be city. And now let's print out ser again, and we'll see we'll get a much more informative output. Here, our column is named city, Bellevue, Leavenworth, Seattle, Spokane, and the name is population. And this series population has data type int64. Now let's move on to descriptive and summary statistics that we can easily get with Pandas series objects. So like NumPy ufuncs, Pandas objects include mathematical and statistical methods. Here's a short list of those that are available. And we'll take a look at a few of these in an example here where we're going to work out some of the similarities between a series and an ND array. So a series is ND array-like, which is not something that I made up. This is very important in the SciPy ecosystem. If something is ND array-like, that means that it's going to behave as expected for an ND array. So a series is similar to an ND array in the fact that it has many attributes and methods that are similar to an ND array. You can pass a series into a method or a function that expects an ND array. And this is the case with most NumPy functions. So essentially what this means is all of those NumPy ufuncs, unary and binary, that we learned in our previous lesson, we can use those with series, which is awesome because all of those great features like vectorization and overloaded operations and broadcasting we saw previously, we can use with series because they are ND array-like. So let's take a look at working through some of these similarities and also trying out some of these descriptive and summary statistics. So let's scroll up and grab our initial series. Here it is, copy, and paste it. Okay, so let's print out ser.shape, which is exactly the same attribute we use with the ND array. So the shape is 4, it's one-dimensional. Let's get the data type, even though we can see it, but it might be nice to be able to store it in a variable. So int64. Let's print out the average for this series, which is 249,777.5. Let's print out this same value that we can get from np.mean passing in ser. We get the same value. So here we can already see how NumPy and pandas are playing well together. Next, let's do a unary ufunc square root passing in ser. So this will do an element-wise square root. So the square root of 1,992 is 44.63. Next, let's take a look at vectorization via an overloaded operator. So let's add ser to itself, essentially doubling our values. So 1992 plus 1992 is 3984. Let's take a look at broadcasting. So let's print ser times 10. So we'll multiply each population by 10. So 10 is going to be broadcast to each element, and we see those extra zeros down this last column here. And now let's take a look at indexing and slicing. So we can index at position 0. So note that I'm not using Bellevue to get 133,982. I'm using a plain old integer location, which is as we would expect, zero-based indexing. Let's take a look at indexing using a list. So let's index at 0 and 2, which will give us Bellevue and Seattle, index position 0 and index position 2. Now let's do Boolean indexing. So let's print out ser sub all the values in ser that are, say, greater than 5,000. So we run this, so we get Bellevue, Seattle, and Spokane. So just omitting Leavenworth from our list. And now let's take a look at slicing. So let's take a slice of ser sub 0 to 2. So this will give us the first two, Bellevue and Leavenworth. Bellevue, and Leavenworth. And let's just take 2 to the end, which will give us Seattle to Spokane.